let's do these ones together. All right, so draw an arrow from the position function, which is d of t, in this particular example, or velocity function, which is v of t. And remember, velocity is the derivative of position. So velocity equals the derivative of the position function, and that's a d. All right, so let's look at the first example. We'll look at each example. The object is at permanent rest. So if something is at permanent rest, it means that the position function has a slope of 0, and the velocity is going to be equal to 0. So that no matter what, it's always equal to 0, right? So when we take the derivative of the position function, we're going to get 0. I think you can see which one this is going to be, because if we take, so first of all, here we have the function d of t equals 6. We know that if we just have a constant value, that it is a horizontal line. A horizontal line has a slope of 0. And if we take the derivative, d prime of t, which is v of t, would equal 0. So the function d of t equals 6 is describing an object at permanent rest. For the next two, right, so moving to the right means that in both cases, the position function has a positive slope, and the velocity function, the values are greater than 0. All right? So here we have a position function and a velocity function. Let's just change them both so that they're velocity functions. Let's just take the derivative here. So v of t would equal, so 1/8 times 2 would be 1/4 t minus 2. So now we have two velocity functions. I think it'll be easier to work with the velocity function, right? So we're going to set, to find out when the velocity is greater than 0, let's set it equal to 0. So we have 0 equals 1/4 t minus 2. Add 2 to both sides, so 2 equals 1/4 t. And then if we multiply both sides by 1/4, squeeze it in here, t equals 8. All right, so at 8, we are, our velocity is going to be 0. All right, well, what happens for values that are less than or greater than 8? Let's make a little sign chart and figure it out. All right, so here is 8, and the velocity there was 0. All right, so what happens if we looked at when t is 1 or when t is 9? All right, so if we plug in 1 into our function here, into our velocity function, which is 1/4 t minus 2, so 1/4 times 1 is 1/4 minus 2, that's going to be a negative number. If I plug in 9, actually let's plug in a nicer number to deal with, because we just want anything, right? It's not going to change. There's only one place where the velocity is 0. It's the only place it can change. So after that, it's going to always be positive or always be negative. So let's just change and take a nice number like 12. So 1/4 of 12 is 3, and 3 minus 2 is 1. That's a positive value. So this means that our function here is moving left from 0. We can have negative time. So from 0 to 8, our function is moving left, and it's moving right from 8 to, whoops, let's fix that, from 8 to infinity. All right, so moving to the right, from 8 to infinity, would be represented by the distance equation, the position equation, 1/8 t squared minus 2t plus 2. All right, and we see we've met the requirement here, so that's our correct function because v of t is greater than 0 for all t greater than 8. All right, at 8, we change positions, we change directions from going to the left and switch to going to the right. All right, let's look at one more, and that's this one. Let's find the, we already have the derivative here, so all we have to do is solve. Well, this one's an easy one to solve. This one is a perfect square, right? It's t minus 8 squared. Right? So we have one solution there at 8, right? And so let's take a look at what happens on either side of that. So when we plugged in 8, that was a 0 for us. And what happens if we take, we'll use the same values, 1 and 12. All right, so if I plug in 1, something less than 8, I get negative 7 times negative 7, right? I could plug it into this one here. And that's going to be a positive 49, so that's positive. If I plug in something greater than 8, right? So I've got 12 minus 8 times 12 minus 8. That's 4 times 4, that's 16. This is a positive number. Right? So notice even though the derivative is 0 at 8, it's going to keep moving in the positive direction. Right? So the only place that we're not moving is that momentary, just that instant at t equals 8, it's moving to the it's not moving at all. Right? So or I guess I shouldn't say it's not moving at all, but our velocity function is 0. So here, this one matches with this one. All right, and that's because v of t is greater than 0 for all t not equal to 8. All right, and of course we don't have negative time, so we start at 0. All right, so here's just looking at direction using velocity. All right, this was an example we saw in the last Nearpod. All right, that's our position function that we graphed, our velocity function that we graphed. The one that I wanted to look at was the speed function. All right, so here we can look at our position function. We start at a stopped position. We're moving in the negative direction where the graph with the position function is red because the slope of the position function is negative. All right, we have a horizontal tangent line. All right, that means we've stopped. And then the blue graph shows we're moving in a positive direction. When the position is in a negative direction, the velocity is negative. So notice that from 0 to 4, the position is going in a negative direction, and the velocity curve is below the x-axis. Our velocity is positive because our particle is moving in a positive direction. The speed graph looks identical to the velocity graph, except the sections below the x-axis are reflected over the x-axis because y values are always positive when we're dealing with speed. We don't look at direction. So now we're going to learn a little bit about acceleration. So acceleration is the rate at which the velocity of a particle changes with respect to time. If s of t is the position function of a particle moving on a coordinate plane, then the instantaneous acceleration of the particle at time t is the derivative of velocity. So a of t is the derivative of velocity. It's also the second derivative of position. All right, so we can either, if we have the position function, we'll take the derivative twice. If we have the velocity function, we'll take the derivative once. All right, so given that f of t is a position function relating distance in terms of time, right, this should be in your notes, that f prime of t is instantaneous velocity, it's the rate of change, and f double prime of t is acceleration. So you should know that acceleration is the change in the rate of change. So anytime you're asked for change in a rate of change, you're looking for second derivative. Right? This is always referring to the second derivative. Acceleration is the derivative of velocity. It's important that you have the right units of measurement. Right? So, a of t is the first derivative of velocity. It's the second derivative of position. If distance is in feet, velocity would be in feet per second. Acceleration would be in feet per second. The rate of change is feet per second. That's velocity. So it's velocity per second. In other words, feet per second, or feet per second squared. Right? Make sure you have the right units of measurement. So if the velocity is 32 feet per second, the acceleration would be 32 feet per second squared. All right? Make sure you have the right units of measure, right? Depending on whether your function is referring to distance, velocity, or acceleration. All right, so let s of t equal t cubed minus 6t squared be the position function of a particle moving along an s-axis where s is in meters and t is in seconds. And that was the one we graphed in the last Nearpod. Find the instantaneous acceleration at a of t and show the graph of acceleration versus time. All right, so the velocity function is the derivative of the position function. The acceleration function is the derivative of velocity. So if we take the derivative of 3t squared minus 12t, we would have, using the power formula, 6t minus 12. Now, if we set this equal to 0, add 12 to both sides, and then divide by 6, t equals 2. All right, so if we look here at our graph, here is the graph of our acceleration function. All right, so this is a of t. All right, so it is it's just a linear function, 6t minus 12. It has a so at 0 seconds, the acceleration is negative 12. Right? At t equals 2 seconds, the acceleration is 0. Where the acceleration is 0, this would be a horizontal tangent. For velocity. So in the next video, we're going to look at speeding up and slowing down. Thanks for watching. Bye for now.